Okay, this is our remaining sort of the last video, I guess, on energy. I'm going to talk about the very important concept of the conservation of energy. And I'm just going to start off by stating something that you've probably heard before, okay? And that is that energy cannot be created or destroyed, only transferred from one form to another. It's something that maybe you learned in middle school, but I don't know if you really know what that means. So hopefully in this course you'll actually figure out exactly what that means. And we're going to spend a lot of time talking about energy transformations and how energy can go from one form to another. It turns out that's super important in terms of solving physics problems, dealing with kinematics. It's going to go back to our previous studies of kinematics. It's kind of tying it all together, okay? This is really a statement of the conservation of energy, and really it's the same thing as the work energy theorem if you think about it, okay? So, for example, consider a normal incandescent light bulb, which is extremely inefficient. I don't know if you've ever noticed how hot an incandescent bulb gets. So for example, if 100 joules of electrical energy are going into this lamp, okay, well guess what? 100 joules of electrical energy have to come out of that lamp because of the conservation of energy. Turns out that about 20 joules are converted to light, if you're lucky, if it's an efficient, relatively efficient bulb. And about 80 joules are wasted as heat, okay? Which is great if it's a cold night and you're trying to heat yourself up with your lamp, but that's really not the point of an incandescent bulb to heat your house. It's to provide light, okay? Another example, a spacecraft being launched into orbit. There's a lot of energy being expended here to get a spacecraft way up high, okay? When it re-enters the atmosphere, you've probably heard about heat shields or seen those cool videos of spaceships re-entering the atmosphere, getting really hot and all that. That's conservation of energy, okay? So that energy, which is actually manifesting itself thermally, can be seen going up and coming back into the atmosphere. It's kind of interesting stuff, okay? All right. Now, consider a ball rolling down a plane, all right, where only gravity does work on it. So it starts up here at the top with an initial speed v sub I, and it finishes down here at the bottom with v sub f. It goes from h, big H, to little h, okay? The work done by gravity to bring it from the start to the finish is mg h minus h, or mg big H minus mg little h, okay? So that makes sense, right? Okay? At height h, the original kinetic energy is 1/2 mvi squared, all right? And at height little h, the kinetic energy is 1/2 mv. This should be f squared, mvf squared, okay? All right, now gravity did work on the ball to speed it up, giving it kinetic energy, and also to drop at a height h minus h, losing gravitational potential energy. It turns out that the work is the same for both. Okay, so the change in potential energy equals this change in kinetic energy, which equals to the work done, okay, by gravity. And that's a really important concept. I'll spend a little more time in class maybe explaining that to you guys, okay? Equating everything, we have that mg big H plus 1/2 mvi squared, okay? This is the sum of the gravitational potential plus kinetic energy at the top. And this is the sum of the gravitational potential plus kinetic at the bottom. Those two are equivalent to one another, rearranging algebraically. Okay? Again, the sum of the KE and GPE stay the same. Turns out they stay the same at all times, at all heights in between. We call this sum the total energy or mechanical energy. Okay? And note that E sub I, the initial energy, is equal to the final energy, unless we're dealing with a non-conservative force such as friction. But unless stated otherwise, you don't have to worry about friction, and we assume that this is particularly the case, which is a statement of the conservation of energy. Okay? Stay the same at all times, at all heights in between. This means that energy is transferred between potential energy and kinetic energy. Now, when something falls, its gravitational potential energy decreases because it's at a lower height, but its kinetic energy increases because it's speeding up. The change in potential energy equals the change in kinetic energy, and this is super useful when solving problems. So you can see this bobsled coming down, okay? All right? If it starts at 0, and we say that the initial potential energy is 600,000 joules, it means that at the bottom, at our 0 reference height, it means that the kinetic energy is 600,000 joules. if that's our zero reference height, because the potential energy would be 0 there. And everywhere else in between, it's a combination of the two numbers where the sum of the KE and PE always add up to be 600,000 joules no matter what. So in other words, the mechanical energy, or the total energy of the system, being the bobsled, remains the same at all heights, okay? This is super useful because we can now determine the speed of an object by simply knowing what its height is, okay? By equating the gravitational potential energy at that height to its kinetic energy and solving for v, which involves dealing with the square root, okay? Remember that the mechanical energy always remains the same, and the total is GPE plus KE. There are lots of other energy transformations, but for now we'll look only at the gravitational potential energy and kinetic energy, okay? All right. This is a PhET simulation, which you should definitely play with, okay? And this is showing that the variation of this skater on this ramp, the variation between the kinetic and the potential, how it's always a trade-off, but the sum of them ends up being the total mechanical energy, which is given by the yellow bar here. It's always the same. Don't worry about the thermal energy. That's not really considered here, okay? Note also that the speed of the skater is highest at the bottom, and it's 0 on the ends, kind of like a spring going up and down. Or it should also remind you of a pendulum, okay? The other thing I want to point out is that when the guy is halfway up in height, that's the point where the kinetic and potential energies are actually the same, all right? But the rate at which the kinetic energy goes up and down and the potential energy goes up and down are not the same, all right? We'll come back to that. It's a very, very interesting phenomenon, okay? So again, study carefully the transfer of energy between these potential and kinetic, and we are neglecting friction, obviously, okay? All right, okay. Example 5, you're probably thinking we did this one before, but this is slightly different. I'm asking you to figure out the speed of the mass at the bottom of the swing if the initial angle is 23 degrees. So you might want to refer back to your work on the previous problem to find the potential energy. To solve this one, go ahead and pause it and try it. This will take you a few minutes, I think. Okay, remember that we found that the height, this height h was 0.00795 meters, and we found that the gravitational potential energy was 0.39 joules. Okay, now, by the conservation of energy, the change in potential equals the change in kinetic. And I can say that the change in potential is mgh minus mg0 equals 1/2 mvi minus 1/2 mvf. Okay, all right. Now, vi is 0. The potential energy on the bottom is 0, okay? Now, so I'm simply equating mgh to 1/2 mvf squared, okay? Notice how I'm not worried about that negative sign again. And I solve for vf, and I get 1.25 meters, okay? Now, I could also have used this fact to do that. I actually didn't use this fact to go this route. But if I do, I get exactly the same answer. Study my solutions and make sure that you understand how I got these taken care of in 2 different ways, okay? I want to point out also that you can find the speed of the mass at any point in a swing if you know the height above the bottom. Super, super useful for dealing with pendulums, and maybe we'll play around with this in class a little bit with some photo gates, and some motion detectors, and see if this actually does work in reality. That'd be kind of fun. Okay. All right. Here's another example, a really important one. Okay. You're faced with these examples all the time. Okay. Go ahead and pause the video and try parts A and B. Okay, so a guy jumps into a pool 3 meters above the water. You're given his potential energy is 6,000 joules. What's the mass of the man? Well, that's pretty easy. It's 204 kilograms. He's a pretty big guy, I guess, because we can equate GPE to mgh and then solve for m. How fast is he going when he's halfway to the water? Halfway to the water, half of his energy has been converted to kinetic energy. So what we do is we just use the kinetic energy equation and solve for v. And I got 5.42 meters per second. Now, you could have also used the Suvat table. And then use an equation of motion. When you do that, you get exactly the same answer. That's so beautiful. Make sure you understand both methods by pausing the video as appropriate. Okay, there's more. How fast is he going when he hits the water, and how long does it take him to hit the water? And sketch a graph of GPE and PE against time on these axes. Pause the video and do it. Especially this one part E is really important for you. Okay, how fast is he going when he hits the water? I got 7.67 meters per second. Okay, you could also have used the equations of motion to do that, I suppose. Okay, but I use the kinetic energy argument. How long does it take him to hit the water? I did use the Suvat table here. I don't know how else you do it. Just under 1 second. And a graph of potential, and this should be kinetic energy. Looks like this, and I want to spend a couple minutes explaining this, okay? So here's my time right here. This line right here corresponds to the mechanical energy of the system, the GPE plus KE. Note how the KE is a concave up curve. GPE is a concave down curve. This point right here is when it's halfway to the water. This is 3,000 joules on the y-axis. Note that this point here, okay, is not halfway between 0 and 0.782. It is not. It's closer to 0.782. Why is that? It's because the object is losing height at an increasing rate, and it's also gaining velocity at an increasing rate, if that makes sense, okay? So that pushes the midpoint of this graph over on the right-hand side, okay? We'll spend a little time going over that in class if you need for me to, okay? All right, here's what seems to be a very easy question. You should be able to do this one after projectile motion. We're going to do it using a kinetic energy argument, and we'll also use the Suvat table. Go ahead and try this one. Okay, using an energy argument, okay? Ball's down here, U is 3, V is 0, okay? It's got a KE max on the bottom and a GPE of 0, GPE max and a KE 0 at the top, okay? I got 0.46 meters by equating these two and solving for H. Doing a Suvat table, look at that. V squared equals U squared plus 2AS. I got the same thing, and I'm going to put a smiley face, because I like getting the same thing when I do the same problem two different ways, okay? Here's one that's a little more difficult. Try this one. Mass rolls, okay. This one's a little more difficult. Pause the video. Okay, I want to point out here a couple of things. On the bottom, KE is at a max and its potential energy is 0. Okay, now the GPE is at a max at the top, but the kinetic energy is not 0. Why? Because the thing is moving. Even though it's not moving vertically, it's moving horizontally. So it's a slightly different problem. On the edge of the table, I'm saying GPE sub T is mgh, okay, and KE sub T is 1/2 mu squared. At the floor, GPE sub F is 0, and KE sub F is 1/2 mv squared. By the conservation of energy, okay, total mechanical energy at the top equals the total mechanical energy at the bottom. Okay, this is 0 right here, and all I do is I solve for V, and I do a little bit of algebra with the square root, and I get 6 meters per second. Okay, this is one about a really cool roller coaster, which I guess is in New Jersey. I've never been there. There's a vertical drop of 127 meters, which is pretty scary. Anyway, try this one. This one will take you a few minutes, so pause the video, especially work on part B until you get an answer. Okay, so in part A, we're neglecting friction and air resistance. Find the speed of the riders at the bottom, okay? At the top, total, okay, this is very similar to the previous problem where at the top, KE is not at a max, and it's not 0, KE is not 0, but it is at a max at the bottom, okay? I got 50.3 meters per second, okay? By a similar reasoning of the previous problem. The more interesting part is part B. The actual speed is 45 meters per second. Find the work done by friction on one roller coaster car if the roller coaster car has a mass of 550 grams, okay? Now E sub I is not equal to E sub F. In fact, EF minus EI is delta E, which is the work done by friction. So these joules that are left over, if you want to think about it that way, that is exactly equal to the work done by friction. So if you think about that, then the rest is algebra. It's pretty easy, okay? E sub F minus E sub I is this expression right here. And then all you do is you plug numbers in. I got 1.4 times 10 to the 5th joules. I retain my negative because I want to be reminded that work is being done by friction, which serves to retard the motion of any object. Okay, so that negative sign is actually quite useful. Okay, I want to talk a little bit to round out this video about other common types of energy transformations. Okay. So for example, if we have water on like a paddle wheel, that's heating water over here. We have gravitational potential energy of the water falling. It's transferred into the kinetic energy of the wheel going around. That then goes into electrical energy, which goes in to heat the coils of the water, which then is transferred into thermal energy, and you have steam. So you see there's all kinds of different energy transformations, and I want to talk about in reality, there is always energy lost to the surroundings. Like, for example, there's friction within the wheel turning around. There's energy lost with the container and the wires, all this kind of stuff, okay? But we very often neglect those energy losses so that we can actually do some physics problems and get some interesting answers, okay? Here's another one that's kind of interesting. So you're heating a kettle, which is then blowing steam on the paddle wheel. So you're going from thermal to kinetic to electrical to thermal. Okay, all right, here's one. This is probably my favorite. The cyclist turning a wheel. Okay, so you're going from chemical, being what she had for breakfast, being converted into kinetic, okay, into electrical, into thermal. And then finally, we have the sun shining on a photovoltaic cell. So we have thermal into electrical into thermal, okay? And this serves to raise the temperature of the water and again produce steam and boils the water, okay? So lots of different energy types of transformations. Really cool PhET simulation. You should play with this one, okay? All right, here's another one. This is exclusively thermal. What I do, I have two thermometers, one showing the iron, one showing room temperature water. I heat the iron to a high temperature. I then put the iron in the water. Look what happens. Okay, there's thermal equilibrium. So again, the thermal energy of the iron goes into the water. In other words, it's heat. Whenever we have a thermal energy transfer, it's called heat. So the iron cools down and the water heats up. Okay, now the same thing would happen if I cooled the iron. If I got the iron really cold, then when I put the iron in the water, the temperature of the iron would go up and the water would go down. Okay, so either way you do it, these are thermal energy transfers, okay? And the transfer of thermal energy is called heat, which you will learn later, and the symbol for heat is big Q in physics.